Hello and welcome to another Solana tutorial. Today I have another very interesting topic for you. Today we're gonna talk about Syscalls. You've probably heard about Solana Syscalls before, and if you're Solana dev, you have used Solana Syscalls before, whether you know about that or not. But today I really want to give you the full package of understanding what Syscalls are, why we need them, what are the different types of syscalls that there are, and then we'll end with why Solana keeps adding new syscalls. Because you might read about that, or you might have heard that Solana once again added a new syscall, and maybe you're like me and you're like, but what does that even mean? Why do we need a syscall for that? And how does that help me as a developer? All those questions hopefully get answered here today in this video. Solana Syscalls. I don't know why I'm excited about that, but it's one of those core things that I feel like I want to understand. So here I am, trying to understand Solana Syscalls. So maybe it's best if we even start out with a high-level overview on what a syscall is. Because we as Solana developers, we write the programs. But those programs get executed kind of in a sandbox, in a VM, where it's just that program that is self-contained. It doesn't by itself get out of this box. It can just execute the code it has. So when we write the Solana program, we compile it, and then all the logic is within the program. And that's what it can use, right? That's for safety measures, because obviously you don't want any user program to be able to just execute code on the validator machine. You don't want the program to be able to escape its sandbox. But sometimes a program might need some functionality that is outside its own code. And that's where syscalls come in. Syscalls allow a program, so a Solana program, I would call it user space program, but that's my OS level thinking, to access resources from the validator through a specific function that we call a syscall, because it's calling the underlying system. And you might be familiar with this from OS level development, from operating systems, where user space programs can use syscalls to access kernel functionality. The kernel being the core of the operating system, and the user space program just being any program that any developer develops. And the calls between them, those are syscalls. And it's the same on Solana, just that it's not a user space program and the kernel, but it's a deployed Solana program and the validator that executes the code. So that's the high level overview. Syscalls are used when a Solana program wants some validator functionality. And there are different types of syscalls, so let's start by having a look at those. Syscall reference, that sounds about right. So we're in Solana docs, programs, syscall reference. Programs interact with a runtime through syscalls. Okay, so I called it the validators. It's the runtime. The validator runs the runtime, and that's what the program is interacting with. So a program interacts with the runtime through syscalls, covering logging, hashing, cryptography, CPIs, and memory stuff and so on. Each deducts compute units from the transaction's shared budget. Yes. So also a syscall costs compute units. We'll analyze it later. For now, let's have a look at what syscalls there are. So here we see where they are registered. So that's then the actual code. So the create program runtime environment, that's where it defines all the syscalls. Here, that's where it registers those functions. Those are all the syscalls that are added. However, this here is not a good overview. Let's stay on this page and check the available syscalls. They come in several categories. Control flow, for instance, if the program wants to abort, there's a syscall for that. Or the cleaner one from a programming perspective is sol panic, that stops the program with a file name, line, and column number for diagnostic. So you panic and you specify where that panic happened. So that's a syscall. There's a syscall for that. Then logging, that's the big one that we use a lot. All of the logs, such that something comes into the program log, all of that needs to go through a syscall. And the main one is the sol log, where you just log a message. So UTF-8 string. There's also one for logging numbers. There's one for logging pub keys more efficiently. And there's logging remaining compute units or arbitrary data. That's the one for program data in the logs. So again, if our program wants to tell the runtime something, hey, log this, make sure that that stays there, you need a syscall for that. Because otherwise the program can just execute stuff and then be done with it. I mean, it does get the input accounts and the instruction data as input, so that comes from outside. It's not like it's fully self-contained, but then it can't get more information unless it's using syscalls. There's two for PDAs, which you have probably already heard of: the create program address or the find program address. Difference being, this one takes all of the seeds you provide and returns you the PDA directly, but it can happen that if you don't provide the right bump, that it's not a valid PDA because it's on curve. So the try find program address iterates through bumps. This one doesn't take the bump as the last seed, but it keeps adding bumps until it finds the canonical bump and then returns that address and the bump itself. So yeah, those are the two syscalls for doing that. I'm pretty sure you used that before, just that the actual syscall hides behind a function of the SDK, so you might not even be aware that whenever you call that function in the SDK, underlying is actually a syscall. Then we have a bunch for hashing, different hashing algorithms, bunch for cryptography, different algorithms or whatever, big integer modular computing some big exponents or whatever. This all used for cryptography, and the reason why we have those, spoilers, is that a native implementation within the program would just be too compute intensive. That's why there need to be syscalls such that a program can actually do it. And we'll look at that later, hopefully. And they actually keep adding more to this list because different applications needed different algorithms. So they kept adding syscalls that those can actually be supported. But maybe also we already say that here a new syscall obviously is consensus breaking. Therefore, it needs to go through a feature gate. Adding a new Solana Syscall needs to be feature gate, needs to be activated. Okay. More syscalls that you're probably more familiar with. The invoke signed comes in two ways. One's for Rust, one's for C. I think just the serialization is different. Both of them do a CPI. So whenever we're doing a CPI, we need to go through the runtime. We need to do a syscall. Then there is sysvars to get certain sysvars, and maybe you've also already heard that some sysvars you need to provide them as an address, like the instruction sysvar, for instance, that needs to be provided as an address, and then the runtime already provides that information within that address, that syscall address, so the program has access to it. But there are some sysvars that any program can get at any time without the address being provided. For instance, the clock sysvar, the epoch schedule, all of those, they can be received through a syscall. So through a syscall, you get the information from a sysvar. And we're actually gonna have a look at one of those, maybe this one. It's a good contender. Yeah, so that's sysvars. Then for memory operations, mem copy, mem move, mem compare, mem set, those are also syscalls. And then the program data stuff, which we've also already used before when we talked about return data in that video. So setting the return data is actually a syscall. That's just how it works on Solana, because the actual return of the program is just okay, or the error code. The entry point just returns a number, so we can't have other return data. So that's handled also via a syscall by saying, hey, that's my return data. And then also getting the return data from a program that we CPI'd into, we need to get return data. And then there's get processed sibling instruction, whatever that means. There's a get stack height. Interesting. Returns the current call stack height. I didn't know that we can do that. Oh, that's actually a great one. Great that I read this. So you can be aware at which call stack height you are. There's a syscall for that. I thought you can't. When would we have needed that? I think when we played with the instruction sysvar, because it flattens all the instructions. We weren't sure where we are. But actually with that syscall, we could have figured out what height we're on. Yeah, anyway, so keep learning. So there's also get stack height. Yeah, okay, cool. So remaining compute units returns the number of compute units. There was also the one with a log that logs the remaining compute units. But if you want to get access to it, there's also the so remaining compute units that gives us the number, epoch stake, and memory allocation, legacy bump allocator. Don't think that's super relevant anymore. Yeah, so mainly the big categories are PDA and CPI stuff, sysvars, logging, and then all the hashing and cryptography stuff that is just implementations of certain algorithms. Yeah. So that's the Syscall reference. Now you know which Syscalls there are, but we still don't know how we work with them. I mean, mostly you don't need to work with them directly because, as I mentioned, the SDKs will just package them for you and it will be ready to be used. But maybe let's do a little bit of lower level programming, still in Rust, but I want to call those Syscalls myself manually. Let's try and do that, just as an exercise, because it's fun. I'm gonna pick a very simple one, like this one, because that should be fairly simple to work with. Syscall log ppf compute units, because it's not... See, maybe we talk about that for a second. When a syscall is called, that's the actual function that is being executed. And we see that this syscall ignores all of the arguments and the memory mapping. And then it calls this message to print program consumption with the remaining compute units. So it's a fairly simple syscall because it doesn't have arguments. The sol log can log up to 5 64-bit values, so it takes all the arguments and then it will log them. The normal syscall log takes the address and the length, so pointer to where the string lives and then how many characters to print, and then it will do the stable log on this with this cost. He just deducts the compute units basically. That's the logging syscalls if you want to see. So the Agave validator client also splits it in those bigger categories: CPI stuff, logging, memory operations, and sysvars. For instance, in the sysvars, the get clock sysvar just takes the address and gets the sysvar get clock. We'll have a look at that later. So yeah, let's build a Solana program and try this ourselves. Okay, how do you build a Solana program? Cargo init, and then we cargo add Solana program, because that's what we want to work with. Oh, we're in version 4. Great. Should I do another... What changed in major version 4? Maybe. We'll see. Then we need to add the crate type. And this is something I keep forgetting often. And then some program code. In this nice docs program Rust, we have some nice example with a hello world that I'm just gonna borrow. Yeah, love it. And then we can build the program. Cargo build SPF. Let's go. Easy. We have a Solana program. Great. And just so we get through the entire cycle, let's also already deploy it and run it once. Okay, I've got some balance, and let's Solana program deploy the target, deploy Syscalls as great. Awesome. In 5 transactions, so it seems to be a very small program. I love it. And we deployed to DevNet. AAVC is my program ID. I kind of like it. Okay, now to call this program, I could write myself a Kit script or whatever. I'll just need a quick script that builds me a transaction with one instruction to that program without any accounts or instruction data. So that's what that's gonna look like. I'm just calling our program, just a program, that's it. So I can deploy and npx tsx call the program. There we go. And from the simulation, we get the logs with the hello world. Can also see that on chain if you want here. Hello world, and 202 compute units are used. And that, by the way, that macro already hides a syscall, right? The sol log syscall is already in there, making it easy for us that we can just log some stuff without calling the syscall directly. However, I want to call the syscall directly because I want to figure out how that's done. So there's a format, and the sol log actually does an unsafe syscalls sol log with this pointer and the message length. So where does this live? Do I have that? No. Syscalls. Oh, we've been here. No, but that's the other side. Repository. Solana SDK. Yeah, that's the other side. That's the one I want. Good. Here syscall. That's the define syscalls. Just for definitions. Okay. Solana defines syscall definitions. Okay, so it takes the definitions and log message. Just does unsafe sol log, which lives where? In the definitions. Cool. So I guess we're just gonna get the definitions of the Solana syscalls and then call them directly. Okay, not sure if I need that config. I will just execute it there anyway. So for now, I'll just include it such that my Rust analyzer doesn't complain. And that is something that I need to import. Cargo add. There we go. So that's the file that we looked at earlier from the Solana SDK, the defined syscall, the definitions just have those definitions. And so the one that I'm interested in is, I want a simple one, the sol log compute units, because that has no arguments. So it makes it easy for me to call. So we're gonna do this. Wait, here it's called sol log compute units. You said it's sol remaining computed. Hold on. Log. This one just calls it sol log compute units. Yeah, I'll just do that. That's what I import. And then instead of this message, I will literally just call sol log compute units, which is an unsafe function. Here we actually see this. Pub unsafe extern C. Nice. That's what it actually is. The actual definition. So first of all, I need to make this in an unsafe block. But then, if I'm like, yeah, I know I'm doing some unsafe stuff here, but trust me, I got this, then I can call the sol log compute units. Let me check if I could actually build and run this. Oh wait, I also need to cargo build SBF and then deploy and run this. It does build. Great. That was the most difficult part. I don't need the message anymore. You're right. I could get rid of that warning. And then it does deploy and voila. Look at this. Transaction went through and we have that many compute units remaining. Why? Well, because we have 200K per default that we get per instruction. So we have one instruction, so we have 200K, and 199,803 is still remaining at this point in the execution. And then it's literally just 3 more low-level instructions for basically returning 0. So we get to the 200. So at this point, we're at 197 because 200K minus this. And then at the end, we're at 200 exactly. That's what this one instruction consumed. Nice. So that's how you call a syscall directly. And if you would have that definition, you could also just say this, because that, again, that's just definitions. I could define it myself like this, then I don't need that. I think I need to do this. Just extern blocks must be unsafe. Okay, make it unsafe. There you go. That I could do. I could say unsafe extern C and then just this. Then I could also call that. And I think it's really just the name that I need. This is nothing more, right? I just define that specific name. And like this, it should do actually the exact same thing. Yeah, look at that. Exact same thing. Cool. But of course, we can make it easier for us and work with the definitions of the syscalls already. But I wouldn't even need to, right? If I don't want to have dependencies for some reason, I would also need to rewrite the entry point and whatever. But also the entry point, we could do that just because I want to, just because this low-level stuff is so fun. Entry point. The Solana entry point has the following signature. Developers are free to create their own implementation of the entry point. So I could, if I really wanted to have no dependencies, be like, yeah, return success. We ignoring the input anyway. This would be the pointer to where the accounts live and then the instruction data and then the program ID, but we ignore that anyway. That's what that parses. So we now have our custom entry point, and in here, since it's unsafe already, might as well call this. I could do that, right? Then I don't need any of those dependencies. And also that, nope. Entry point out of bound. Oh, do you need a return 0? Try adding a return type. Yeah, you have a U64 return type. Can I then still have the implementation? So this is what the actual entry point does, right? Let's look at that. Oh yeah, but yeah, essentially it also doesn't do anything else than this. Do I miss the no mangle? Huh! Look, I'm not actually sure what that does, but it seems like, hold on, get completely rid of the dependencies now, and it still builds. Wow. Okay, so that's how you try the program without dependencies at all. I literally just need to know what the entry point is called, and I need to know what the syscalls are called, and that's it, right? That's the incoming things, and that's the outgoing things, essentially. Although also the outgoing things, they will come back with something. That's functions, right? That's functions, and that's the function that's being called in the very beginning when the program is executed. And those are functions that I can call to get access to other stuff. That's it. Syscalls and the entry point. And again, it does the same thing. This time, even more efficient because I threw out the standard entry point and all the account parsing stuff. And I literally just call the sol log compute units. So that's 101 compute units here and 103 in total. There you go. Now you know. My point was, this is the same stuff that we're doing here, essentially, just manually defining, hey, that's the name of the function. Yes, it's extra and C, it's unsafe, but yeah, that's it. And those functions that we define here, those we call, because when a program is executed, it has all of those functions. If we call them, the program doesn't need to have them implemented. The program just needs to have the correct name, and then the runtime will know, oh, this is a Syscall. We just need to match the name. As soon as I have an unmatching name, let's see what happens then unresolved symbol. It doesn't know what that is. So even already when we compile it, the error shows up. Interesting. And don't ask me where it actually checks that. But anyway, the point is you need to have the correct name, and then you can call the syscall. Great. Should we stay with this? I guess why not, now that we got rid of all that other stuff. At the same time, I do think that importing this is the correct way to do it and not to define it yourself, because that just also makes it easier so you don't misspell it and you can find the correct syscalls here. But yeah, you could define it yourself. Let's do the same with the other one, with the other, if you wanted to work with numbers, not the log, but the sol remaining compute units. This is not the one that logs it, but that gets me the number. So the signature looks like this. It doesn't take arguments, but it gives me a number. So if I wanted to do it myself, I would need to write unsafe function, this name, no arguments, but returns a number. Then I could also call it like this, and now I'm not gonna log it, but I'm gonna get remaining compute units from this very function. We just call that function. That's a U64. And well, what do I do with this now? I can't really return it. Then I would return an error. So if I wanted to actually log this, oh well, guess what? There's more stuff in here that we can use. More syscalls. Sol log or sol log 64, which can log 5 U64s. So if I wanted to define that myself, I would need to say unsafe function sol log 64 with argument 1, which is a U64, argument 2, 3, 4, 5. And what does it return? Nothing. And now we have it doubled again, so it's red. But like this, I should be able to actually log this. It takes 5 arguments. So let's see if I would sol log 64 just my remaining. That's just not even the correct definition. So to make it work, I'll just add more numbers. Call to unsafe needs an unsafe block. Let's see, does it compile? No. Oh, already sol remaining compute units. I think it doesn't see that because it's not in an unsafe block. Nope. Hold on. Nope, it just doesn't like sol remaining compute units. Interesting. Why? That's the same thing as if I misspelled it earlier, right? Aren't all of those ending with an underline? Nope, also that it doesn't have. Okay, let's look. The log compute units and sol remaining compute units. I mean, looks fine to me. Is that not implemented yet? Is that not live yet? Solana program, compute units, sol remaining compute units. And also syscall sol remaining compute units. That's it. Maybe I should go back to the regular entry point. Maybe that helps. So it seems like for whatever reason, my cargo build SPF doesn't like this. Where are we? We're in Solana 3.1.2. Let's just in case get the newest version. That wasn't a major update, so I don't think that will change anything. Nah. Okay, I can't get this to work. Doesn't matter. We're just gonna accept that we can't get the remaining compute units and not go there. Let's just not go there. But just for testing, would logging those 5 numbers work? Yeah, that looks good. And the program log would say 0x0x because it logs 5 numbers. Okay, and if I would define it my own way and just have 4 numbers, what would happen then? I'm really curious. I actually don't know. Either it's not a valid function that can be called, but it did compile, so maybe it just ignores the other arguments. And yes, interesting. It doesn't make it 0 because we're in C. Whatever happens to be on the stack or wherever we are, yeah, probably on the stack, whatever happens to be there will be an argument that we take. So again, this is unsafe, literally, because if you don't provide the arguments, but the function actually takes the arguments, welcome to C. we're not in Rust anymore, then it will just take whatever is there. So basically, don't define it with the wrong arguments. It's probably a really very bad idea. You probably do want all of the 5 arguments, otherwise it might take random stuff. And the Syscall just happens to force you to log 5 numbers, so there you go. That's what you gotta do. But anyway, I do want to work with a syscall that gives me something back though, because those two, they're just logging stuff. I want to get something. So let's do a more sophisticated one. If we can't do the one with the compute units, let's get one of the sysvars. Oh no, the get clock sysvar is deprecated? Why is it deprecated? Use sol get sysvar with clock sysvar address instead. Okay, this is deprecated. You shouldn't get the clock sysvar with get clock sysvar, but they have the generic get sysvar is the one you should use. And that needs the sysvar ID address. For that I need to know where that sysvar lives. Oh, that makes it more complicated. The result pointer, and then I can specify offset and length. Okay, one step at a time. I'm gonna first use the deprecated sysvar, because it's just deprecated, not removed. See if I can get that to work, and then in the next step I will get it to work properly, non-deprecated. I mean, obviously, I could also just use the program SDK and be like clock, and then I could say clock get, right? There was the function that gets me the sysvar a result for Solana Syscall. Load the sysvar directly from the runtime. Clock, and I could unwrap this. There it neatly gives me which epoch we're in, which slot we're in, and I could, you know what, let's log this. Why do we have the sol log? Let's log the epoch, clock, slot, and Unix timestamp. Why not? What else is there? Epoch start time. What else is there? I still need one. I'll do a magic number just so I have something. Okay, those are not the right types, as if I might. Again, this is yellow because it's unsafe, but I think it will work. We are running out of space. Solana program. Extend this thing for at least this many bytes, maybe more. Can't be bothered to constantly extend it. So here you go. Try that again. We're at 15 transactions now, so obviously the program was too small. Okay, see, that worked. px nice. And we logged all of those things that don't really mean much to me, but we see that's a realistic number for an epoch. That's a realistic number for a slot. Those are realistic numbers for timestamps, where this one should be slightly smaller than this one, and it is. And that's my magic number. That checks out. So again, it's not the nicest formatting because I'm doing the sol logs, but hey, therefore we're pretty efficient. And I could get the log message, the sol log, and build a proper string first. Should we do it as an exercise? I could also just use message, but that feels like it's cheating. No, I'm too lazy. I'm just gonna use this. This is just for our debugging now anyway, just so we get it a bit more readable for us as humans. It doesn't like alloc free. Why does it not like that? Where did I even import that? Something is really weird now. What if I don't do that? The sol alloc free, wasn't that the deprecated one that we saw in the very bottom here? The sol alloc free, disabled for new deployments, only available to programs deployed before the feature gate. So it makes sense that's not available anymore. But then why are we importing that? Or is that because we imported this thing? That would be weird. No, it came from the message, didn't it? Yeah, this is just so weird. You know what? Screw this. We can manually verify that. Fine, if I can't properly print it. We're in epoch 452 in hex, so that's 1106. Let's quickly check where we actually are. On DevNet, we're in epoch 1106. We're in this slot. That's the slot. So decimal 478134. 478134. So that checks out. I can just log the values in hex. Fine. Because what I actually wanted to get to, and I'm getting so sidetracked here today, but it's still fun, for me at least, I hope for you too. By the way, it's a challenge to try and figure all the stuff out that I didn't manage to figure out in this video, and then tell me, hey, that's how you do it. I'll be grateful for that. Or just for you to learn. Because this is just, it's a little bit weird. But I'm still on track to continue my base understanding of sysvars So now I'm not gonna take the clock sysvar here like this with a SDK unwrap. How boring is that? I wanna do it myself by getting the clock sysvar, which is deprecated, but it's still easier than the other one. So we first try to get this to work. So the way it works is it needs an address, a mutable pointer, because that's where it writes that to, right? That's where it writes the sysvar contents to, I think. So we need a address that is a, wait, so no, the address, so we need the data on stack. And now we need to know a little bit about the sysvar to figure out what it stores. And if we have a quick look at the sysvar data, here for the clock sysvar, the layout is the following. It has the slot, the epoch start time, the epoch, the leader schedule, and the Unix time. We already saw all of this when we actually used the clock with the SDK, but now we want to do it manually. So basically U64, 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 U64. So 1, 2, 3, 4, 5 times 8 is 40. So we need 40 bytes. And can I just say this? So I just say, hey, this exists now on the stack. I don't need to write anything there yet, right? So it's just on the stack. And then I get to have the address. I get the type cannot be deferred address, which is just a s-mutable pointer, and then put the address here. Data isn't initialized. Okay, fine. Then we initialize it here. Have 0 40 times. Ah, there we go. That looks better. And then the get clock sysvar writes the sysvar data into here, so into those 40 bytes. So then I could read the things again. So first is the slot. That would be a U64. So U64 from little endian bytes, because we have just bytes here, and it's the first 8 bytes from the data. So 0 to 8 like that. Found U8. Okay, then we need to try into maybe something like that. That should work. Then we have the slot. What else do we want? The epoch and the timestamp. It works all the same. Epoch, timestamp, just that we're at different parts, because the epoch is the third one and the timestamp the fifth one. So it's 16 to 16 plus 8. I'm lazy. And the last one is 4 times 8 until 5 times 8. Yeah, I'm lazy, but it will replace that with actual numbers anyway. So, and then we log the same thing with the epoch, the slot, and the timestamp. Start timestamp. I didn't read. I could also, if I wanted to, because that's the second one that's between those two. But nah, I'll just, that's enough. Let's see. Can we actually work with the clock sysvar? Compiling, deploying, and calling. Yeah, look. And that looks similar. Look at that. 452, which was our epoch, and that's our slot. Nice. Still checks out. So we now read the data from the clock sysvar directly. Honestly, this is pretty low level, but yeah, we're not using that many compute units. And honestly, if you would write a Solana program, that's not how I recommend that you do it, obviously. Use the SDK and not unsafe external methods, the functions directly. But the main point here just being, this is how that works in the background. This is what the SDK is hiding from you. A syscall. Okay, but that syscall is deprecated. Maybe we shouldn't use it. So let's just get sysvar and see how we can use the get sysvar. But with a get sysvar, it's getting a little bit more complicated, because now we need the ID address as a const U8 pointer. So basically that's the sysvar ID that we need to have saved somewhere. Then the result I'm expecting to be the same as we just had here with the address, and then offset and length if we wanted to provide that. Okay, shouldn't be too difficult. So basically we replace this with this. The address was the second argument. The ID is the first argument. I will say offset 0 and length 40, because that's how many bytes we want to read. And now the ID, that's the important part. Where would I get that from? I could, of course, import that from somewhere. Clock sysvar ID. Function to an address, address. Could I theoretically have this here and this just reference? So we need a raw pointer, freaking raw pointer. This is an address. What's behind that? I think address is just type, right? And what's behind that is really just the bytes. So the bytes is what I'm interested in. 2 bytes get s pointer. Ha ha ha! Freaking genius. Look, I just get the bytes as pointer, and then I put the clock sysvar ID here. Do you think that's gonna be the same? Do you think that even compile? It does compile, and it does also work. No, it does not. We are at least not getting the same values, which is good because it means I'm not making the mistake that I have the same as before. It shows that it's not the same as before. So we now know that I'm doing something wrong, and now I need to fix it to get the right values, and then we can be sure again that it's actually from here, from the get sysvar. Okay, what's happening here though? The get sysvar, it returns a U64, and the U64, it returns, what does it return? I'll also log the result here for myself. Oh, we do get warnings. This pointer will immediately be invalid. Yeah, that's not good then. And we get 0x2, whatever that means. Okay, what if I put that in here directly? Is that the same issue? Do I get the same warning? No! And I get the right values. Cool, so the pointer was immediately dropped because the bytes were not actually stored somewhere, because it makes it 2 bytes but then drops it again. So if we do it here, then it's fine. Great, nice. And like this, we also get the right values here. Still in hex encoded, but that's fine. And now the return value was actually 0, the result here. 0 for success. Love it. Yeah, so that's how you do the syscall of sol get sysvar, and that's how you get the clock sysvar. You can also hardcode the bytes if you don't want to be dependent on any dependencies. We could do that, right? I have the ID here, and I could be like, instead of the ID here, I could be like let clock, and then just say clock sysvar ID as pointer. That should also yield the same thing, right? Yep. And then we're not dependent on any other crate. So I now just hard coded it in here. That's the clock sysvar. And if anything changes here, if we have a different address, then we will probably get the error 2 again. So the return value of the sysvar, yep, probably for invalid address or whatever. And then I don't get anything written into my data. Yeah. So make sure if you're doing this that you're actually checking the return value of this syscall, because if it's non-zero, then it's an error, and you can't just expect that it has been written into your data. Okay. Good. I mean, that's pretty solid for working with syscalls, right? I think this is a good place to end. We did get a better understanding of what syscalls are, how we can call them manually. We saw that there are a bunch of different syscalls, and we saw how to call them manually. What's still open is the discussion on why they keep adding more syscalls and why there are so many cryptographic syscalls. Isn't that just algorithms? Why does that need to go through the runtime? Spoiler alert, the answer for that is efficiency. And I wanted to have a look at that in this video, but it's already long enough, I think, that I will talk about this in the next video, which you can check out here, and also another one right there if you want to. I enjoyed this journey today. If you did too, give me a like, subscribe if you haven't done that already. I just love learning about that low-level stuff and really understanding what's happening behind the scenes. It is a bit strange sometimes, especially when stuff is getting deprecated or when new stuff is coming along that is not yet fully there but already kind of there, but then you don't know how to really use it, like we had with the remaining compute units that I wanted to get as a number and didn't manage. But yeah, it was an interesting journey. I really enjoyed this. I really enjoy learning about Solana development and just trying stuff out. So you go ahead and try stuff out yourself, and then I will see you in the next video talking more about Solana Syscalls. Until then, bye bye.